So I'm going to present some work I've done together with a few people named Amit. They're all here. Um, it makes for very confusing email chains, but we're working on it. Um, I guess I want to start by apologizing to any biologists in the audience. What we've done to model continuous heterogeneity for our toy problem is taken one of Fred's very nice maps and butchered it and essentially turned it into continuously moving molecule by just taking one part and rotating it. So this may not be very biologically plausible, but it turns out that you can get some interesting results just playing with this type of data. So we have a continuously varying volume here, and I don't need to tell you all that this is something that is an interesting problem. This is something that we want to try to figure out because often we'll have molecules that move in a certain way, and the way that they move can have an effect on the function. And so this is something that biologists want to find out. So the way we're modeling it is basically what Joakim Frank was talking about yesterday is we're thinking that we have some sort of parameter space on a manifold, and that a point on that manifold maps to a specific volume that we're interested in reconstructing. So in this case, we have pure rotation movement, which means that our manifold is just a circle. It's a one torus. But you can imagine having a 2D type of movement where you have two parameters or three and so on. Like this type of manifold can be anything, really. But here we're considering something that's relatively straightforward, which is just a circle. All right. So to formalize this a bit and give some notation, we have theta, which is our parameter on the manifold, that we map to a volume, which is x. So x is a function of theta, and x is something that lives in an L by L by L cube, so density map. We take that, we have some direction, some projection direction, and we project that density map, and we get some image. We apply CTF, we apply noise, we do all these things, and we get something like this. So this is, as you're all familiar with, this is what the data looks like. And so for the rest of the talk, I'm going to assume that we know a lot of things about this forward model. I'm going to assume that we know the rotations, that is the viewing directions, the CTF, the translations, and so on, which we get by running this through Relion or some other model and getting a consensus estimate. And for what we need to do, this seems to work pretty well. All right. So in this model, what we have is these images. We know P, we know a little bit about the noise, and we want to be able to reverse this to some extent and get the manifold back. And we want to, in particular, for each image Y that we have here, we want to know where on the manifold it fits to kind of relate the images together. All right. So the way we're going to do this is by way of going to very low resolution and seeing what we can do there. And by very low resolution, I mean taking these images and binning them to something like 16 by 16 images. And there's a reason, we'll get to the reason why we do this, but the first thing that we can do with this is we can construct a mean volume. And this looks pretty bad, right? This is not something that you can say a lot about. It doesn't look much like the structure that we had previously, but it tells us a little bit about where the densities are. And here where we have the rotating part, we see that a lot of stuff is averaged out because the density essentially goes down, and the only thing that's left is the middle part where we actually have density in all different states. All right, so why are we bothering with low resolution? Well, it turns out that if we want to do something like covariance estimation, we need to work in low resolution. Because if the images are L by L, the volumes that we reconstruct are going to be L by L by L, which means that the 3D covariance matrix of these volumes is going to be L cubed by L cubed, so L to the sixth. And so doing a quick calculation, L to the sixth grows very fast, which means that if you have something like images that are even 32 by 32, this thing becomes very difficult to store on a normal machine. 64 by 64, forget about it. So if we are to do this covariance estimate, we need to work at low resolution. But it turns out you can still get a lot of important information this way. So I'm not going to go into detail about how we do all this estimation, but essentially they're least squares estimators that we apply to these images. And again, we assume that we know the rotations and so on, so we can formulate it as linear least squares and optimize it that way. Once we have an estimate of the covariance, we can do a lot of things. We can estimate, we can look at the eigenvalues. We can take the diagonal of the covariance, we'll get a variance map. There's a lot of different things we can do, but here we're going to focus on the eigenvalues and the eigenvectors. And an eigenvector of the covariance here is a volume, so we can call them eigenvolumes. And so this is something that has been looked at for a while. I think Joakim Frank was one of the first people to look at this in a 95 paper. Pavel Penchek has done a lot of this, and Fred also a little bit recently, 2014, I think there's a paper. So this kind of idea of looking at eigenvalues is not new. So in this particular example with this toy data set, we have two eigenvalues that stand out. And this is a little bit exceptional. And part of the reason is that we're working with very low resolution, and we also have a C4 symmetry in the moving part. So we only get two eigenvolumes here. And so if we take a look at these, they tell us something interesting about the movement. So the first two eigenvolumes, the leading eigenvolumes, have this pattern here. So gray is the mean structure, blue is positive part of the eigenvolume, and red is negative part of the eigenvolume. And so as you take the mean and you add these two eigenvolumes together, you're able to replicate part of this rotational movement. So it tells you a little bit about how the actual structure is changing throughout the data set. And these further eigenvolumes, it looks like they're mostly noise, they're not containing much information, so we can actually throw those out. And you can kind of see that from the spectrum. These things dominate, so they're probably what we care about. All right. So what can we do with this? Well, if we have an estimate of the mean, a low resolution estimate, still low resolution, we have some estimates of the eigenvolumes, what we can say is then if the covariance matrix is like this, where we have a few eigenvolumes that dominate, we can approximate the volume x as a linear combination of the mean plus some of these eigenvolumes with some coefficients that we don't know. And if we take this and we project, remember, we assume that we know P. We know the rotation, we know the CTF. We can create a synthetic image from this volume. We get a similar model for the actual images, the projected mean, and then a linear combination of the projected eigenvolumes. So we can take this and we can fit the betas to the image. So essentially what we'll have is this. We'll have a very noisy Cryo-EM image. We'll have the projected mean, again at low resolution, and then these low resolution eigenvalues, and we can combine and get an estimate for the betas. And so even if this thing is very noisy, it turns out we actually get a good estimate on the betas because we only have a few eigenvolumes or projected eigenvolumes that we're fitting. The noise here is isotropic. It goes in all directions. But we only care about a certain direction, few directions of variability, so we can actually estimate these betas pretty well, even in a very low SNR environment. So then we can go back and say, okay, well, we'll go from the images, we'll go back to the volume. Since the betas are the same, we can take the mean volume plus these eigenvolumes, combine them, and get something like this. All right, so we're still very low resolution, but we see here that we have captured some of the movement in terms of the rotating part of this fake molecule. All right. So what can we do with this? Like I said, this is very low resolution. There's maybe not a lot of interpretability, but one thing that we can do is now that we have associated the low resolution reconstruction with each image, we can talk about distances. We can say this image is closely related to that image and closely related to that image based on their low resolution reconstructions. Now these images don't have to be in the same viewing direction because we've created a reconstruction for each one of them. And so essentially you want to compare these low resolution reconstructions, but since they're all parameterized by these betas and the space is orthogonal, it's equivalent to looking at the distance on the beta coefficients. So you have image I, image J, you get this squared distance between them. And you can take these, you can look at the nearest neighbors. This is the image that we had just before, and these are different images. If you're used to staring at Cryo-EM images, you can see that the noise in these is actually slightly different. They're not the same image. But once we do the volume, the low resolution reconstruction, we get something very similar. So it tells us that this image is actually closely related to this image. And we can continue doing this, and we can build a whole graph over all of the images. So we have n images, we get a graph with n nodes, and the edges correspond to kind of this distance measure that we get from these low resolution reconstructions. And the reason that we want to do this is because the edges in this graph, or the graph as a whole, actually tells us something about the underlying manifold. If two images are close in the graph, we expect the corresponding points to be close in the manifold. And this lets us apply a lot of powerful manifold learning techniques. So we can take these distances, we can construct an affinity matrix, a weight matrix. We can use this to construct a graph Laplacian, which is the discrete graph analog of a regular Laplacian on a manifold. And we could play with this. In particular, what we want to do is we want to take the eigenvectors of this Laplacian. So these things, if we have n images, this is an n by n matrix. L is an n by n matrix as well. Again, it corresponds to kind of some approximation of the Laplacian on the manifold. If we have a function on the manifold that is essentially a vector that has a vector with a value at each point on the graph, at each image, then we can apply L to that function on the graph, and we get what's essentially the Laplacian on that graph. So these eigenvectors are also going to be functions on that graph. For each point, we're going to have a value of these phi's. And in particular, we can look at the low-frequency eigenvectors, so the eigenvectors that correspond to the smallest eigenvalues. Now, if you look at a regular Laplacian in Euclidean space or on a manifold, the low-frequency eigenvectors or eigenfunctions are going to correspond to very slowly moving sinusoids. And this is going to be the case on these graphs as well. So we can take the first few, and those are going to give us a way to parameterize the manifold. They're going to give us a set of coordinates. So if we plot this for the values that we have for this synthetic data set, we see that we do indeed recover this manifold that we had at the beginning. We recover the same topology, the same circular structure. And for each image, we can associate it with a point in this space. And so this is something that's been done for a while in manifold learning. These are known as Laplacian eigenmaps. There are other related, very similar methods called diffusion maps and so on that work very similarly by working with the graph Laplacian. So this gives us an idea of what the manifold looks like from these images. Through the low-resolution reconstructions, we can construct distances, and from that we can get this parameterization, which is nice. But what can we do with this? Well, for one, we could look at something like an energy landscape, like what Joakim was talking about yesterday. There's another thing that we can do is we can get out of these low-resolution reconstructions that we have. Because now that we have an idea of what the manifold looks like, we can say, well, these images are similar, so maybe we can reconstruct them together. Maybe we can take this node here and take all the other images that correspond to some similar reconstruction and apply regular full resolution reconstruction to these things. So this is going to be very expensive, right? For each one of these points, or for some set of points, you're going to have to do a reconstruction, and you have to choose the size and so on. So this can be a bit difficult. And we're going to take a slightly different approach. We're going to go back to the eigenvectors of the graph Laplacian. So as I mentioned, in the continuous case, the eigenfunctions of the Laplacian correspond to Fourier modes. In particular, the lowest frequency eigenfunctions are going to be the lowest frequency Fourier modes. And so this is going to be the case on the graph as well. So if we just take the values of phi1 and phi2, it's relatively trivial, it's just going to map out the axis. It's not going to tell us something very interesting. But this is a very low frequency function on the graph, right? It's the only thing that's lower frequency is the constant. And so the constant function actually exists too. It's phi0, but I'm not going to plot it here. But we can increase. We can say phi3, phi4. Now we get more oscillations. This corresponds to a period that's twice that of phi1 and phi2. And they're also coming paired, right? You can think of this as a sine, and this is a cosine. They're shifted by pi over 4 in phase. So we get essentially a basis of smooth functions on this manifold. So we can represent smooth functions by linearly combining these phi vectors, these eigenvectors. Oh, and we have another one too. So blue here corresponds to negative values, and red corresponds to positive values. All right. So why do we care about this? Well, it turns out that we have one particular function on the manifold that we're very interested in, which is x. Again, if we go back to our model, we're parametrizing x with theta. That's a value on the manifold. That's a point on the manifold. And so in particular, each voxel, if we take our rotating structure and we isolate a voxel and we see what the value of that voxel is as we go through the manifold, as we vary theta, that's a function on the manifold, right? And it's going to be a smooth function if that movement is smooth and we don't have too much high frequency things that can upset it. So this is what I picked a voxel that looked interesting, and this is the type of function that we have. So in certain areas here, it's negative, and then it's positive here, and in between, there's not much happening. Actually, this is probably 0, and this is positive, right? So we have this is some voxel where part of it is coming in, and then it's coming out. And we have some other ones, but in general, they look pretty smooth. So what we can do is we can say, well, since we have a basis of smooth functions on the manifold, smooth functions of theta, we can do a linear combination. Let's say we take the first R eigenfunctions, where R is not a huge number. We can fit some alpha to that, so some set of alphas to that expansion. Now, this is going to be the case if we look at the whole volume. The whole volume is a vector-valued function on the manifold. So we can just put all of these together. We get 1 alpha for each voxel. So we get a bunch of these coefficient volumes, these alphas. So we can go back and do what we were doing before. We can say, well, now we have a model for the full resolution volumes that's parameterized by these eigenfunctions, and we can project them to get a model for the images. And then we want to apply that to all of the images in our data set and try to fit these alphas. This is, again, is a linear least squares problem. In the degenerate case where R is equal to 1, we get normal tomographic reconstruction, because when R is equal to 1, the phi here is constant because it's phi 0. So we're essentially, we have 1 alpha that we're trying to estimate, and it corresponds to the mean. It corresponds to just a least squares estimator. But as we increase R, we're reconstructing these weighted volume estimates. So we get a generalized reconstruction problem. And this is a lot of coefficients, right? Each one here is a set of voxels, and we have R of them. R can be something on the order of 10 or 20. But it turns out that we can actually do this relatively fast by using a particular forward model that's a sum of complex exponentials, like a non-uniform Fourier transform. It turns out that we could solve this iteratively relatively fast. There's a small constant here. But normally for a reasonable sized data set, like 100,000 images, maybe working with images that are 100 by 100 and not that big, it'll take a couple of hours. So it's on the CPU. We're currently working on porting this to GPU. All right, so what do these things look like? So as I mentioned, the 0th one is going to look something like the mean. And we have some decent structure down here because this part's not moving. And then we have here, since we have movement, we get something very blurry. But if we look at the spectral volumes, so these alphas, we're calling them spectral volumes, which will make sense in just a few minutes. We have the positive part and the negative part alternating just like we saw before. So here we're essentially reproducing the low frequencies that were captured in the covariance eigenvectors, but now we're getting these more finer structures here as well because we're working at higher resolution. And so we can get an expansion that actually gets us higher resolution structures. And in a sense, what these are is that they're coefficients, they're Fourier coefficients of the volume of each voxel as we go around theta. So that's why we're calling these spectral volumes. In some sense, they represent the Fourier transform of the volume function as you move around the manifold. And you can prove some results on this in certain situations where you have uniform distribution of viewing angles and you have a lot of images. We can see that these alphas actually correspond to something reasonable, which is taking the actual volume function and taking it in a product with these eigenfunctions. It turns out that we can get some reasonable estimate of these things. Noise still plays a role, but it's doing something sensible. All right. So now that we have these spectral volumes, we want to go back and look at the reconstructions, right? So we can plug this into our model. We get an x hat, which is our estimated volume. And from an image then, we're able to go to these low resolution estimates. And now by finding these spectral volumes, by finding this expansion in terms of these smooth functions on the manifold, we get something that's a little better. We have some blurriness here, but we're only using 4 spectral volumes. If we increase the number of spectral volumes, we're able to recover something that looks a lot more like the original. I don't have the original map here, but you can see that there's a lot more detail that we recover here. And we can look in FSC of these things. Since we have the ground truth, we can just compare it with the original. We see we reconstruct. It's not completely crazy. I'm not very excited about this, but we're working on it. All right, so this is all. very exciting, but it's on synthetic data, right? So we recently started looking at experimental data recently, and we have some preliminary results. This is a data set from Grant Jensen's lab. We have some noisy images here. This is the mean structure that we reconstruct and rely on. And so I took the threshold relatively low here so that we wouldn't miss certain parts. But essentially, you have some movement here in the sides. And I should say this is an aldolase coupled with, actually it's 4 aldolases coupled with a DARPin. And the idea here is that there's some wiggling here that we want to try to capture. And so if we take this, we run it through the pipeline, we get some estimated eigenvalues. And this is a very low resolution mean then, and then we have these eigenvalues that are popping up around. And we see that basically whenever we have a red next to a blue like this, that means that we have a positive part next to a negative part, which means that it indicates that there's some sort of movement happening here. But there's also some things happening out here which we're not very excited about. But this is very preliminary stuff. I think actually these came in yesterday. So, all right. So let's look at the type of manifold that we're estimating here. And so here we're plotting the 7th eigenfunction and the 14th eigenfunction, because it turns out that the lower frequency eigenfunctions don't actually show all that much interesting stuff. We think that there's some variability that's spurious in the sense that you may have changes in contrast and so on between the different images that it's picking up, but it's not necessarily interesting in terms of conformational variability. But if you look at certain pairs, you see that there's definitely some structure that's going on there. Most of it's concentrated here, but we have some movement out here. And if we look at the corresponding spectral volumes, it's a bit of a mess, but if we zoom in here, we see that we have the mean volume here that's kind of buffeted by these 2 positive and negative parts of the spectral volume, again showing that there's probably some movement here. And there's a little bit of that happening up here. And so if we look at the actual reconstructions, here are 2 reconstructions that we get from the data, we see that there's a lot of different things happening all at once, but there's maybe some movement going on here, but obviously there's still some ways to go in terms of experimental data. And that's kind of the challenge right now is looking at what can we do to improve these things by regularization, by focusing things. So part of the reason that we get a lot of this noise, that we get a lot of this other stuff happening, is that we're not really putting any priors on here. We're not saying, oh, this variability should be localized in these regions, or it should have a certain smoothness. The only parameters that we're putting in is how many eigenfunctions are we using to describe this manifold function. So that poses some smoothness conditions. But otherwise, we're just kind of estimating these volumes. So part of the work going forward will be implementing priors and making sure that these things don't pick up too much noise. Because when you're estimating 16 volumes instead of 1, noise gets spread out a lot more. So that's something that we're looking at. All right. But the take-home message is that these types of methods with low-resolution reconstructions, while they may not be always very interesting in themselves to actually look at the volumes, they can still carry a lot of information in terms of the similarity between the corresponding reconstructions of the images. And in particular, we can look at estimating manifold structure using these graph Laplacian type techniques, and that can actually get us some useful information. And yeah, so as I mentioned, we're currently working on improving a lot of things. The running time is okay, but we'd like it to be faster with GPUs and so on. We think that we can get significant speed up. Looking at things like regularization and focusing in on areas, because we know that there are certain areas that should be static and probably are mostly contributing noise to these spectral volume estimates. But also alternating the refinement of the manifold, because once we have these high resolution reconstructions, one can imagine estimating the manifold anew from these things and going back. But also looking at other things that's less strictly in this kind of framework, but energy landscape, and trying to estimate if there's some way that we can parameterize the motion that's happening in these things. So these are all things that we're working on. So that's it. Thank you guys very much for listening.